Right, so hello everyone. So Reid asked me to give maybe a gentle introduction, or so I hope, to the sort of viewpoint on expansion, on higher dimensional expansion in particular, that sort of, in a sense, historically at least preceded maybe the spectral one, at least much of it, and that is more sort of motivated by geometry and topology. And indeed, my background is in computational topology and applications of topological methods. So anyway, my understanding is that many of you may not be working with cohomology on a daily basis. So I thought I'll start with a basic introduction. So let X be a finite simplicial complex. So just a finite set system, closed undertaking subsets, as we have seen many in many of the previous lectures. That just means that we can kind of decompose X into layers where this is just the empty set. X0 is the set of vertices. X1 is the set of edges, or pair, which is a certain set of pairs of vertices. X2 is a subset of triples, and so forth. Let me draw one more. We have certain incidences between these, just given by the containment structure. Now, in cohomology, you essentially look at an algebraic version of this, and the simplest one that I want to focus on is you look at vector spaces over the field with two elements. And then topologists call these cochains, or sometimes chains, but I will call them cochains. So let me introduce this notation. Ck of x, which is really the same as Ck of x with Z2 coefficients, is just what I just wrote there, Z2 to the xk. So these are just functions from the K simplices. Oops. Z2. Okay. Now, we have incidence relations, which we can think of as bipartite graphs between adjacent layers. And these naturally give rise to linear maps between these vector spaces of functions. So I should say these are called cochains. And these linear maps are called co-boundary operators. Maybe I should use a different color because it gets overloaded. So this thing is called a co-boundary operator. Maybe too fancy a word. And it's just given by the incidence relation, but let's spell it out. So if we have a function in, let's say, a k-1 cochain, so a function from k-1 simplices to Z2, then what is its coboundary? It's a function that eats k simplices. And so k simplex is a certain subset of k plus 1 vertices, which I will label V0, V1, Vk. And so what does it mean? That it's the linear map that's given by the incidence relation, so by the matrix that encodes the bipartite incidence graph. Well, it just means that if I have this k-simplex, I look at all the k-1 simplices that are contained in it, and I sum up the values of my function on these. So I throw one out, topologists would put a hat here. I'll just cross it out. Okay, so that's the definition of a co-boundary operator. So far, so good. Let's look at a few examples. So for instance, if f is in C minus 1. Yes?
This is the same as the down operator we talked about.
Well, it would be the up operator, with the difference that you kind of, okay, so here I haven't yet, this one doesn't depend on any probability distribution, which is one different, but morally speaking, it's essentially that.
No, but the coefficients are in Z2 and not real value.
That's the other main difference, yes. But I will come to that. Everything, yeah, sorry. So this is really as a function mod 2. Thank you very much for, so let me stress this, mod 2. Yes. Okay, so let's see. If f is in here, then it's just a function that assigns 0 or 1 to the empty set. So it's just a constant. And then delta of f eats a single vertex. And it's the same constant on every vertex. Okay, let's do another one. Well, let's number these. If we have a zero-dimensional cochain, so that's just a 0, 1 valued function on the vertices, or in other words, a subset of vertices. Then delta f of, let's say, an edge uv is just the sum over the endpoints. Again, mod 2. So this is 0 if the two values are the same and 1 otherwise. So in other words, it's, if I think of, this is maybe this is f equal to 1, and this is f equal to 0, then this is delta f. It's just a cut defined by this function. Let's maybe do one more. So if f is in C1 of x, so that just means it's a subset of edges. And then delta f of a triangle, let's say UVW, is just I take my function on the edges and I sum it up mod 2 over the 3 edges. At some point I'll forget writing the mods to it. Okay. So now it's an easy exercise to check that if I take the co-boundary in some dimension, I should really use indices, but they get cumbersome. So I start in some dimension, I don't know, I go up 1 dimension to I plus 1. And then I do this again, so I go up to dimension I plus 2. This is 0. The reason is the following. So what I really do is I end up in subsets of size, let's say I plus 2. So I will have some set S union two particular vertices. And then I will do this twice. So in the first operation, I would go over all subsets that have 1 element less. And then I would sum again over all subsets that have 1 element less than that. So in the end, I will sum up over repeatedly, in a certain sense, over subsets that have 2 elements less. And for each subset that has 2 elements less, I have 2 ways of going down. I can either first remove A and then B, or the other way around. And because I distinguish these 2 ways in the way I'm summing up, I get 0 modulo 2. So this means that the kernel, or the image of, the image of delta, let's say, from ck minus 1 of x to ck of x is contained in the kernel of the following co-boundary operator. And so these images, these are called co-boundaries, k-dimensional co-boundaries. And the elements in the kernel are called cocycles. And because I have, so this is a linear subspace, this is a linear subspace. I have this containment, so I can form the quotient. Okay. So let's do one little example. Let's look at this simplicial complex, which has 6 vertices, despite of what you might think you see. So this just means that the things on the boundary are identified. So this is the same vertex as this. This is just an easier way of drawing the simplicial complex so that you can see what's going on. So this means that I have 6 vertices. I have actually, if you check, you can easily see that I have all the 6 choose 2 edges, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 triangles. Okay. So let's look, for instance, at this one-dimensional cochain. So remember, a one-dimensional cochain is a 0, 1 valued function on the edges, or a subset of edges. What is its co-boundary?
Every triangle is incident to an even number of edges. So
right? Exactly. Right. So these triangles don't see any red edges, and the ones in the middle see 2. So that's it. So this is actually a one-dimensional cocycle. On the other hand, I can ask, let's look at this definition of cohomology. So here I would look at the cocycle. So this is definitely a cocycle, modulo the coboundaries. So if I look at this thing as defining an element in cohomology, I can ask myself, is it trivial? That would mean, so it's definitely a cocycle, but is it a coboundary? Well, in this case, we can easily check. Let's suppose it is a coboundary. This means it would be the coboundary of some set of vertices. Well, let's look at this vertex. I mean, definitely some of the endpoints have to be, well, they all have to be assigned values. The coboundary, the cut across the edges across a cut of vertices doesn't change if I flip the sides. So I can assume that this side gets 0. Then clearly this vertex needs to get 1. Then this one also needs to get 1. This one needs to get 0. This one needs to get value 1, and this is turning black. And this one needs to get 0, but this is already a contradiction. So this means that this particular one-dimensional cocycle witnesses the fact that my complex has non-trivial first cohomology. So many of you, at least those who have done a bit of simplicial cohomology will know that this is the projective plane or a triangulation of the projective plane. So this space actually has first cohomology exactly equal to Z2. So there's a single generator. But anyway, but that doesn't matter first. Okay, so that's all good and well. Of course, you can ask, why would one care? Well, okay, one answer is that cohomology is a fundamental notion in topology and mathematics in general. Let me maybe give you a slightly more concrete motivation. So, as I mentioned, I work in all sorts of questions related to the intersection between combinatorics and topology, or combinatorics and geometry. And one basic question or one basic type of problem that often occurs is that you have some simplicial complex that somehow encodes your combinatorial problem, and you look at maps from this simplicial complex to some Euclidean space. So, I mean, a very basic version of this that you can think of is you have a graph, and you might want to draw it in the plane with maybe as few crossings as possible. But so let me just consider a map. And for simplicity, let me assume that the map is linear to some Euclidean space. So by this, by a linear map, I just mean I map the vertices somewhere, wherever I want, and then I interpolate the rest linearly. So an edge would be mapped to the segment joining the two endpoints. A triangle would be mapped to the convex hull of the three endpoints, and so forth. But everything I'll say will work more generally, but just for simplicity, let me focus on this. So for instance, since this was so popular, let's look at the fish complex. So this could be X. And then my map, well, I don't really know. There are many things that I could do. So in particular, I mean, I just want to illustrate that I in no way want to assume that I have an embedding. So maybe I map these vertices like this, and then maybe I fold this one like this. So if this is A, this would be f of A. If this is B, this is f of B. So this would be my f. Okay, why not? All right. So the reason why I mention this is because I want to give a bit more geometric meaning to the notion of cochains and co-boundaries and co-cycles. So let's consider a point that is in some sense generic or in general position. So in the plane, for instance, a generic point wouldn't end up lying on the image of a vertex or on an edge, because if I wiggle, that goes away. But it could very well end up in the interior of a triangle, maybe here. Or maybe here. I don't know. Let's say this is P. So P all right. And now what I want to look at are all the simplices, let's say the D simplices, whose image contains P. And I will denote this by f sharp of P. You can imagine that this sharp is a weird way of writing -1. So this is like the inverse image. But for various reasons, I don't want to write f inverse. So this is just a set of D simplices such that. Okay. So this is, I've defined it here as a set, but of course this is the same as a cochain with C2 coefficients. So I assign 1 to the D simplices that contain this point and 0 otherwise. So note, and that's kind of the main point of this remark, f sharp of p is actually a co-boundary. Okay, so let's see why this is. The reason is the following. So you take your point and you pick your favorite ray that emanates from this point to infinity. Let's say this one. I keep misplacing my pen. And suppose again that this ray is kind of generic, meaning in the plane, I don't want it to pass through any point. Or in general, rho should not pass simplices of dimension d minus 2. Well then, I claim that f sharp of p is the co-boundary of f sharp of rho, which is the set of all d minus 1 simplices intersecting rho. Right? Because if my point lies in the interior of a triangle and I go to infinity, I have to cross the boundary once. If it doesn't lie in the interior of my triangle, then either rho will miss it entirely. So for instance, rho misses this triangle entirely, or it might encounter the triangle, but then it has to go in and out again because I wasn't in there to begin with. Okay. So you can play this game in much more generality, as I said. So instead of a linear map, you can take an arbitrary continuous map, or let's say a piecewise linear map. You can subdivide your complex first and then map it. You can also, instead of a single ray, you can think of some more complicated curve that escapes to infinity, and the same reasoning will apply. Ray. And it's actually not hard to show that if you allow this greater generality, then you can represent any co-boundary this way. And anyway, any d minus 1 dimensional cochain whose co-boundary it is. All right. Okay, so far so good. Now, okay, that's about cohomology and cochains and co-boundaries and co-cycles. But what does this have to do with expansion? So higher dimensional expansion is a way of quantifying all this. So it's a way of quantifying the fact that, for instance, the cohomology doesn't vanish or vanishes one way or another. So let's first look at graph expansion. And this is closest in spirit, or this is actually what I want to discuss, is a higher dimensional generalization of edge expansion. So let's look at that first. And I want to talk about edge expansion in graphs that are not necessarily sparse.
Is this kind of geometric property the reason we chose Z2 as a field to work with? I mean,
yes and no. So you can actually define everything I've done here also with other coefficients. It just becomes more complicated. But indeed, there are some geometric applications where, for instance, I want to really count things like the number of simplices that hit a point. And then Z2 is the right coefficients to work with. I might say something about this later. So for instance, you can, instead of Z2, you can work with integer coefficients. And then what could happen if you allow more complicated maps is that, for instance, a triangle gets folded or wrapped around. Folded is not a good point. But imagine that you take a triangle and you do something like this. Then if you look at the point, it turns out that the right thing to say is not just that this triangle hits this point, but that this triangle hits this point with multiplicity plus or minus 2, depending on orientations. And it depends on what you want. Sometimes you want to consider maps and you consider all preimages with multiplicity, and sometimes not. The other reason is simply that over Z2 you really get an immediate generalization of edge expansion. Okay, so let's recall edge expansion. So a graph with vertex set V and edge set E has edge expansion, at least eta, where this is some parameter. If the following holds, well, for every subset of vertices, you look at the co-boundary, just the edges going between S and its complement. And I want to talk about the non-sparse case, or possibly non-sparse case, so I normalize. And I want that this is at least eta. Well, what? I can't just compare it to the size of S, because I might have a very large set. So the right thing to do is either I take S or I take the cardinality of its complement, because it doesn't matter. This is completely symmetric. Oops, and this is not vertices, but edges. And here normalized to the vertices. So in other words, I mean, this is a normalized way of talking about edge expansion, where I assume that I have the uniform distribution on both the vertices and the edges. And this kind of makes sense. Okay, so let's generalize this. So as we saw earlier, this is the same as a function that eats vertices and spits out 0 or 1. Again, this is just a Hamming norm. What is this? So let me write double squares for the normalized Hamming norm. So what do we really do here? Well, we either take the norm of S normalized, or we take the norm of S complement. But this just means that I take the minimum of F.
So
Delta is,
delta on the left-hand side, sorry.
Sorry, thank you very much. Yes, I want to measure the co-boundary. And here I compare to the size either of normalized size either of F or of its complement, which is the same as F plus the constant 1 function. What this really is the minimum, in very fancy terms, of all ways of adding a zero-dimensional co-boundary to my function. There are only two, either the constant 0 function. Okay.
So your x is g here. Your x is g here.
Yes, x is g. Thank you. Indeed, my x is g. Okay, so now, once you have this formulation, it's kind of formally, just symbolically immediate how you generalize. Let me maybe just introduce one thing that we might need, or maybe not, but anyway. Okay, so let's say a simplicial complex. Let me leave a bit of space. So a simplicial complex X has co-boundary expansion at least some parameter eta in dimension k, more precisely for the co-boundary that goes from dimension k minus 1 to k. If the same thing holds. So for every k minus 1 dimensional cochain, I want that if I look at its co-boundary and I look at its normalized Hamming norm, then this is at least my expansion factor times the normalized Hamming norm of f, not quite, times however small I can make the normalized Hamming norm of f by adding a coboundary. Of the same dimension. So this is my defining inequality. And the one last thing, let me just maybe write the notation somewhere where so this I will use for the normalized Hamming norm. Another way of saying it that maybe so here I would just say, if I take the standard Hamming norm, I would just say I count how many ones my cochain has, and I divide by the number of possible ones, which is just the number of simplices of that dimension. More generally, in the spirit of what we have been doing and seeing in the previous talks, you could assign some system of weights to the simplices of your dimension, of the dimension you're looking at, that sum up to 1. In other words, a probability distribution. And then this would just be the expected weight of f of the simplex, where the simplex is drawn from the probability distribution. Now that probability distribution might be uniform, then you get the standard normalized Hamming norm. It might be this kind of Garland type distribution that propagates downwards that we have seen in the spectral case, or it might indeed be anything. So with respect, there's kind of some choice of norm in the background. All right.
We in fact know that we need to work with the same thing as the Gala.
Say again?
I think in all what is known, we need to work with the same normalization.
No, not at all.
Okay.
No, there's for instance a result like for the constructions of expanders, one usually works with this, at least the existing constructions. But for instance, there's an alternative proof of a result in discrete geometry, namely the number of Tverberg partitions, that you can prove using a very different norm. So let me maybe just mention a norm that might look stupid. Suppose you have a bunch of n-element subsets. This is not the layered structure of a simplicial complex. I just want to describe a simplicial complex, which is also a matrix complex. And suppose which you label V1, V2, V3, and all of them have, let's say, size n. You could, for instance, you can look at the simplices, which is just subsets of the union of these vertices that contain at most one vertex from each. So this could be, for instance, an admissible triangle. And one norm that turns out to be useful on the k-dimensional cochains is to give weight to 0 to all the simplices, except the k-simplices that only use vertices from the first k plus 1. Okay, it's very much an aside, but just to give, that turns out to be a useful norm, and it's very different from the norms that we usually see. And it turns out that that has a useful application, which I will not.
It's like just allowing those subsets as part of your simplicial complex?
No, you can't, because then you don't get a simplicial complex. You want to get, for a simplicial complex, you need, for instance, if you want to have top-dimensional simplices, they would be transversals. If you want a simplicial complex, so this would be a face. So you need to allow as a subset, for instance, this face. Otherwise, you don't. But I want this face to have 0, weight 0. OK, anyway, sorry, this is very much a distraction. I didn't mean to talk about this, but oops. Right. OK, so this is the definition. At least one example. and I should say, sorry about this, that this definition arose independently. They didn't call it that way, but in a paper by Nati and Rui, and independently in a paper by Gromov. They didn't use this name, but I like the name, so I will use it. Okay. And the example is also due to them. As Pladat says, the kind of the sanity check should be whether the complete object is an expander. And indeed it is. So this thing has co-boundary expansion 1. And this is not trivial. It's not hard, ex post facto, once you see the proof, but it's not trivial. Let me see. I have about 15 minutes left. Let's take it on faith for now. So for the complete graph, you can...
No.
It's
a different story.
What was the name?
Boros
No, Boros-Füredi is related. That's actually what I want to say something about.
Uli,
Yes?
you want to say how it's related to cohomology?
I will. If I'm not running out of pen. So let me come into this. Yes, so remark. Expansion. If I have a complex that has expansion greater than 0 in dimension k, this implies that hk minus 1 of x is 0. Just like edge expansion implies that my graph is connected, which means that h0 disappears. Let's say two-dimensional expansion larger than 0 implies that the first cohomology disappears, and so forth. And it's a quantitative version of this. Why? Well, let's look at the definition. If I have a k minus 1 dimensional cochain, its coboundary is large compared to its, you can think of this as the distance to the space of coboundaries. But that means that if I have something that is not a coboundary, it has non-zero distance. This distance is multiplied by something positive, so that's still positive. So the norm of its coboundary must be positive, so it's non-zero. So therefore, anything that is not a coboundary can, so that cannot be a cocycle. All right. What else did I want to say? Okay, so there are essentially 3 things I want to mention. Indeed, I want to say a few words about topological overlap and Boros-Füredi. I wanted to say maybe a couple of words about other coefficients, which I will skip because we already touched upon that. And I wanted to also draw a connection to... Let me do another aside. Inspired by what we saw earlier. Okay, so we define this for a simplicial complex. Okay, but if you look at the definitions, we don't really need a simplicial complex or anything. All we need is that we have vector spaces over Z2. We have something that we call a coboundary map. And we have some notion of sizes. And the expansion just says that we need at least 3 vector spaces. We look at the middle one. We look at coboundaries of things in the middle one. And we want to say they are large. If whatever thing in the middle we look at doesn't come from something 1 layer down. in short, what I want to say is just that you can also think of this as some kind of property testing. So in the example that we saw earlier, let's look at linearity testing. So there we had some vector space, z2 to the n. We had, let's call this v. We had another vector space, which were the functions from v to z2. And we had a third vector space that were the functions from pairs of elements of v to z2. So we can put them into a diagram like this, where here we just take a vertex and we map it to the function that eats an element and just sends it to the linear, so this just is the linear function defined by v. And if we have any function, we can send it exactly to sort of the test whether it's linear locally. So this should be something that eats a pair, and this would just be this expression. And now what we saw earlier is exactly that when we are, so the image of the first delta defines the linear subspace, the linear functions. And linearity testing just says that if we are far from that, then our quote-unquote co-boundary must also be large. So this co-chain complex, if you will, is expanding. Okay. All right. What else do I want to say? Yes, so I wanted to talk about topological overlap. All right.
So just one question, all the
Yes.
definitions you made make sense even if it's not a simplicial complex?
Yes, so all you need is essentially that you have vector spaces, you have linear maps between subsequent ones, so this would be, and what you usually want is that, you know, the composition of two subsequent ones is 0, so that you have some notion of cohomology. So such a thing would be called a cochain complex over Z2. The other ingredient you need is you need some kind of norm, which you typically specify by specifying a basis in each dimension, and then you can think of the Hamming norm. You can do it more generally, but that would be the most sort of natural way. And that's an example. This thing doesn't come from a simplicial complex, but it's still a chain complex. In fact, an exact one that has expansion.
So in this,
So the relative choice of bases in the different things would matter, like, for the expansion?
It wouldn't. Okay, this might matter. I mean, one nice thing about simplicial complexes, for instance, is that if you think about these properties, like for instance about the property of being a co-cycle, the property that my own co-boundary vanishes, this is something that where you need to check only, you know, a bounded number of bits. Yeah, I mean, definitely, the notion of expansion depends not only on the vector space, on the linear structure, but on the choice of. You need to have some. It's a quantitative notion, so it depends on the notion of size or norm that you impose. Okay. What else did I want to say? Yes. Okay. Topological overlap. Let me maybe erase this. So here's a result by Gromov that I think convinced a lot of people. I mean, it was in his paper, among others, that this notion was introduced, but I think it also convinced a lot of people who are maybe not so interested necessarily in topology to begin with, that it's a very interesting concept. And the theorem is the following. Suppose X is a simplicial complex. And that we can say something about the co-boundary expansion in dimension 1, 2, and so forth up to some dimension d that we like. Then, for every map, and let's say the only thing I want to assume here is that so I want to assume that the distribution or the norm on the top face is uniform. Then for every map of this complex, there exists a point.
Here you assume continuous, right?
Yes.
Yeah, map, you mean continuous.
Map, I mean continuous. Yes, sorry.
One line before the last.
Every continuous map from this complex to R to the D, there exists a point that is heavily covered. Is at least some constant, and I can even try to see if I remember it or find it in my notes. I had written it down somewhere. Yeah. So the fraction of top-dimensional simplices that will hit this point is essentially the product of the expansion factors times 1 over d factorial. This is not sharp. We don't know what the answer is. But when Gromov's proof gives something that's actually by a factor of 2 larger, but never mind. But when he published this, this was better than anything that people had known, even in the special case of linear maps and the complete complex. And even for the complete complex, the optimal constant is not known. So there were earlier results by Boros-Füredi, as mentioned, and Barian and others that showed that there was some constant, but even this was surprising. And definitely no previous proof had said anything for continuous maps.
So for complete complex, do we know it should decrease exponentially in D?
It has to decrease exponentially in D. But it should, the common conjecture is that it should decrease exponentially in D, not in D log D. The example is that you can have in mind, even though I'm lying a little bit, but anyway, partition your vertices into D plus 1 equal clusters that you place at the vertices of a regular simplex, and that's your linear map. So in the plane, you would map your complete 2-dimensional complex. You would map n over 3 vertices here, n over 3 vertices here, n over 3 vertices here. And one can show that you can't essentially do better than putting a point in the middle. Right. So exponential decrease in D you can't do anything about, but it could be something like e to the minus d instead of 1.
So one other thing, we don't know anything about connection between graph expansion and a spectral expansion, spectral HDX, right?
You mean high dimension expansion and spectral? No. So, I mean, there are some connections, but what is definitely not, so for graph expansion, at least if you have, say, a regular graph,
No, even for non-regular graph you have it. That's a Chigger inequality.
You have a Chigger inequality, but you have to be a bit careful. But you definitely. What?
I think this is just asking for like bisections for graphs. Like Chigger's.
No. This would be sort of bisection width. This is really edge expansion. And for very irregular graphs, anyway, it doesn't matter. What is definitely true is that in dimension 2 and higher, spectral expansion does not capture co-boundary expansion. However,
this is not expansion. The geometrical topological
overlap is weak. Some people call this topological expansion. This follows from co-boundary expansion, but it's not equivalent.
All dimensions. Topological expansion in all dimensions.
Well, up to the dimension where if you have co-boundary expansion in dimension 1 up to D, you get topological expansion in dimension 1 up to D. So for maps into R1, R2, R3, and so forth up to R to the D. But the other way around, it's definitely false.
And take two expanders of a half n and no edges between them.
That's right. So, and indeed, there are weakenings. So, as Nati says, so to get this, you don't really need expansion. Like the simplest case of this is D equal 1, which says if you map a graph or any complex onto the line, there exists a point whose pre-image intersects a positive fraction of all edges. And that, of course, stays true if you have two large cliques or something like that. And there is a corresponding weakening in higher dimensions, which goes under the name of cosystolic expansion. That is still sufficient. And even that is stronger than, it implies topological overlap, but you don't need it. You can weaken things further. But anyway, so.
But you want to say something about the boundary expansion versus spectral expansion?
Right. Right. So it's definitely, okay, so remark 1. Remark 2. Okay, we have seen some version of spectral expansion. There are different versions of spectral expansion that for instance, capture real cohomology, where you essentially do everything the same, except that working over Z2, you work over the reals. And instead of using the Hamming norm, you use an L2 norm or a weighted L2 norm on cochains. And then doing exactly the same thing, you get a notion of spectral expansion in terms of higher dimensional Laplacians.
You have to use orientation there so that...
Over the reals, you have to use orientations, yes. But anyway, neither that version of spectral expansion nor the version of either of the versions of spectral expansion we have seen implies co-boundary expansion. But there are results due to, so let me write spectral expansion.
You're saying it doesn't imply, so there are counterexamples?
Yes. So I can, it depends. So one counterexample is a probabilistic construction that I don't really have time to describe. I can explain it offline, but you can construct, for instance, a two-dimensional complex, even with a complete one skeleton, where the link of every vertex is as good a spectral expander as you could possibly hope for. It essentially looks like GN1/2. But still, the whole two-dimensional complex is not a co-boundary expander. And that example, for instance, will have all possible spectral properties that you can hope for with the optimal eigenvalue gaps and so forth. So spectral expansion does not imply co-boundary expansion. However, sorry for those who are sitting in the corner. I don't know where else to write it. I will put it here anyway. What?
You could move the board.
I can move the board. Yes, excellent. If only somebody had mentioned this before. There are what you could call local to global results due to so by Tali, David Kastan, Alex, Shai, and others, that show that some notions of spectral expansion or sufficiently strong spectral expansion for the underlying one skeleton and also for all the links imply something very related, which I'll just call expansion on small cochains, which is the name that these authors use. Which means that, oops, aha, it doesn't move that way. Which means that you get a property like this, but you don't get it, morally speaking, for all f. You only get it for f's that are not too large. And once you have this property, does it? No, there's a screw here, unfortunately. Or maybe it stops even before. Anyway, and if you have this property, and if you additionally know some further information, for instance, that your complex is the two-dimensional skeleton of a three-dimensional Ramanujan complex or something along these lines, you get furthermore cosystolic expansion, which I mentioned here but didn't explain. And from that, you get, for instance, examples of bounded degree simplicial complexes in dimension 2 and also in higher dimension that have this topological overlap property. Yes?
Don't you need the links to be co-boundary expanders? It's not just the spectrum.
Yes, I was lying. That is true. You need the links to be co-boundary expanders. I was hoping to swap this and sweep this under the carpet. I wanted to tell a story, but you're completely right. Okay. That's right. So in short, one thing we know is that we know that there are sort of very sparse cosystolic expanders and therefore very sparse complexes with this property. But for co-boundary expansion, the story is more complicated. And in particular, spectral expansion cannot give it. Yes?
So so here is a different way to look at this thing. I don't know if it has anything to do with co-boundary expansion. So we can look at the this high-dimensional walk we were here
right.
last talk. We can build up a graph, right?
Right.
That you have a vertex for every d-dimensional face.
Right.
And you connect two faces if they intersect at d-1
Yes.
dimension. And you can study the expansion of this graph.
Right.
And basically from a spectral expansion, you get that the spectral gap of this graph is about 1 over d.
Right.
It says that the expansion of this giant graph is not so good. It's like about like if you just Shiger's inequality on this giant graph, it's about 1 over root d or d or something like
right.
that. Whereas what you can prove is that this graph is actually a small set expander. So if you look at the small sets in this giant graph, they actually expand. So it seems to be some analog of this thing going on with a different language, this language of...
Why?
Why? I also
it's a co-boundary expansion, right? So it's also saying that for functions which have big norm, you don't expand. Function for a small norm, you expand, which is like a small set expanding. So
just that, but the boundary expansion is different from...
I know I'm not saying they're the same, but maybe there is something... I don't know, maybe something can be said between the expansion of that graph and this language. I don't know, it just seems very...
skeptical, but I don't know.
Maybe. I just want to mention that here there is a trick that Tali, Alex, and David found out that if you expand small sets, then essentially you're expanding all of them except for the top dimension. So there is this pesky thing that if you have a 100-dimensional complex and you know you're expanding small sets in all 100 dimension, then you're completely expanding except for the, like, up until the 99 dimension. So I think you get something slightly stronger than your situation. So that's what enabled us to get the cosystolic. Cosystolic is not just small set expansion, it's really all expansion.
Maybe I can at least say it in words. It's cosystolic expansion means actually a co-isoperimetric or an isoperimetric. Well, actually, I shouldn't say this because I'm using more words than I should have. Anyway, never mind. Let me not say it. There was another question by Yotam.
So spectral expansion doesn't imply coboundary expansion.
Right.
Can you say something about the other way around?
Good question. I can't. Definitely. It's also, I mean, it's maybe not so surprising because if you think about the graph case, the fact that spectral expansion implies edge expansion is essentially a triviality, because spectral expansion is something like the canonical semi-definite relaxation of a combinatorial quadratic optimization problem, and it's a triviality that it provides a lower bound, but the fact that it provides also an upper bound, or that it's related, you need to work a bit. I mean, you need essentially spectral partitioning, which is, there's some idea there. And in higher dimension, I don't know. So the short answer is I don't know if there is an implication in the reverse direction. I'm a bit skeptical, but I don't know.
A question on the norms. So even there, when you define edge expansion, usually for Cheeger you would define like conductance. So the norm on the vertices would be proportional to the degree.
Right.
So I'm wondering if the fact that you allow like different norms here makes co-boundary expansion a harder object than spectral.
No, so all the problems I mentioned, like the counterexample and so forth, for instance, the counterexample that I mentioned regarding co-boundary expansion versus spectral expansion, it's essentially uniform. So it just gives you more flexibility, and there are some applications where this is useful. But as Tali mentioned, so this kind of the analog of the norm that you mentioned, where everything is induced from the top dimension, this is, for instance, what is used for these constructions. I mean, I think it would be, even just restricting to this norm, that comes sort of from the trickle-down norm or whatever we want to call it. We don't know how to analyze it properly.
More questions?
Yeah, so this co-boundary expansion definition looks a lot like some kind of like local testing type.
Right, it is local. It's a property testing properties.
Examples where this is kind of I guess you had the linearity testing example,
right,
which is something like this. But are there other examples where you can cast known like property testing results in this? So
Tali and Alex have a paper on this. Where I think you discussed some more examples, but I don't remember. I mean, as you said, so here you have the property of being a co-boundary. You can kind of test by looking at the co-boundary of what you are. But so I don't remember. Yeah, I don't know of something sort of really radically different.
Are there any constructions of this co-boundary expanders which are at like constant degree? So there's nothing.
No, so there's none. But one other thing I should mention, which I forgot. So it depends on what you mean by constant degree or bounded degree. So if you want every vertex to be contained in a bounded number of simplices of all dimensions, then essentially no, the best sort of constructions give you complexes that are of strongly bounded degree in the sense that have weaker properties like cosystolic expansion. However, there are constructions due to Rui and Alex Lubotsky and due to Lubotsky, Zurluria, and Ron Rosenthal, I think, of complexes that are sort of weakly bounded degree. So for instance, of two complexes that have a dense one skeleton, but where every edge is contained in a bounded number of triangles, and the same in higher dimensions. So weakly bounded degree in this sense that exists, but even there, I think so these are randomized constructions, and I think in a sense the analysis is a bit unsatisfactory. I mean, these are beautiful results, but essentially they use ideas related to this to prove expansion on small cochains, and then they use measure concentration results on the large cochains, which requires you to understand very well sort of the tail bounds that you get for the particular distributions that your probabilistic construction provides. But it's sort of, so in a sense, I would say we don't have a really good criteria that imply co-boundary expansion. Not everybody might agree, but
if you're willing to be willing to accept a two-dimensional co-boundary expander, then condition on some well-believed conjecture in number theory, in the paper of Tali and Alex and David, at the very end they had something saying that that there exists two-dimensional co-boundary expander with boundary degree.
Conditioning on the
log n degree, is there something
Oh, log n.
log. You mean but you mean vertex degree or everywhere? So that seems more feasible, but I don't know of a construction that would yield it. Like, essentially, I mean, there is. I should say there is another paper by Izal and Tali where they give a sort of so these constructions here are based on Ramanujan complexes. They give a different, simpler group theoretic construction, which, as far as I know, we still don't know that they're co-boundary expanders, but we hope. So there might be, but I think in general, it's like if you really want fairly sparse complexes, there is no good random model, as far as I know, not even with like logarithmic degrees. Simply because, I mean, it's kind of hard to construct something where if you look from a vertex, okay, that's fine, but then you need to make sure that there are enough kind of triangles, there are enough edges that form triangles with these emanating edges. So I don't know.
Isn't the Nati and Roy random like a complex model give you
but they have full
degree?
scale.
Yeah, but that's a full k-1 skeleton.
And
So you have
Very far from being sparse.
Okay, I think we should probably
Okay.
have a little bit of a break. So reconvene at 3:30 for the last topic.